Now that we are just about done with the derivative portion of calculus, I thought that we would tackle some AP style problems. Right, we have already actually been tackling many AP style problems. However, we have not tackled one that would be in the same format as on the AP test. On the free response portion of the AP test, there are 6 free response questions, and each of those questions has a value of 9 points. So when we have a lot of times that free response question will have like 4 or 5 different parts to it. And a lot of times the parts are somewhat unrelated. So although we've done parts of each of the AP style problems, we've never just chunked them together into one problem. A lot of times they'll have some sort of function and just ask us all sorts of different topic questions about that. So we have to get into the just pattern of being able to change our brain from one topic to another very quickly and easily about a topic. So that's what we're going to be looking at today. I'm going to be doing problems 1 and 3 in your note packet with you, and then you'll get to practice problems 2 and 4. So here we go. All right, hopefully you have a calculator out for this one. You can just kind of watch me through it. I will be kind of showing you what I get on my calculator, so if you just want to follow along with me, that would be great. This one says let f be a twice differentiable function with f of 1.5 equal 3. So that was nice that they told us some information. And then they also say that the derivative of f, sorry about that one. Bamboo tablets, a little crazy here. Stop. Okay, the derivative of f is given by f prime of x is equal to the quantity 7x minus 19 times sine of the quantity x squared minus 4x plus 4 for the interval 1 to 4. Okay, so first of all, A says to find all values of x in the interval 1 to 4 at which f has a critical point. Classify each as the location of a relative minimum, a relative maximum, or neither. So we are looking for where f has a critical point. Well, we know f has a critical point when f prime is equal to 0 or f prime is undefined. All right, so we basically want to take this derivative right here. So we're going to take 7x minus 9 sine x squared minus 4x plus 4, and we're going to be setting that equal to 0. Okay, well, solving that could be somewhat of an issue, but fortunately we do have our calculator. So we are, and we'll call this f prime, we are going to be using our calculator. So I took the liberty of graphing this function so we can have, because we know if we have an f prime picture, I think we're getting pretty good at telling where critical points are and making an f prime chart from that. So that is what I'm going to do. So I'm going to draw an f prime chart here, an f prime picture. Please notice that the picture only goes from 1 to 4. So I changed my window to just go just from 1 to 4. So if you change your window to do that too. I also changed my y max and min just to go up to 4, from -4 to 4, just so otherwise it kind of still looked like a squishy picture. Okay, so when I did that, my picture looked something like, it bounced right here, it came up like that, and then it came back down like that. All right, so if I'm looking for where does f prime equal 0, since this is f prime, I'm looking for where does the graph touch the x-axis, which is there, there, and there. And so then I did the calc, and then I looked for zeros. So I used the 0 feature of my calculator, and my critical values were x equals 2, x equals 2.714. Please remember we do have to go 3 decimal places when we do these problems. And then x equals 3.772. Okay, the next thing that I did, because it says we have to classify the location of each of those as a relative minimum, maximum, or neither, I went ahead and drew my f prime chart because I think that's easier to look at. So f prime, I have 2 on it, I have 2.714 on it, and I have 3.772 on it. So when I'm looking at this, because I am f prime and I'm looking at f prime, we are going to be looking at above and below. So the graph of f prime is below the x-axis till it gets to 2, so f prime will be negative. It stays below till it gets to 2.714, so that will still be negative. And then between 2.714 and 3.772, f prime is positive because the graph is above the x-axis, and then the graph falls below the x-axis again, making f prime negative. So if I'm asking, first of all, at x equals 2, I notice that f prime does not change sign. So I'm going to say if it has maximum, minimum, or neither, it has neither, and then it does say to justify. So I'm going to say because f prime does not change sign. Okay, then x equals 2.714. Before 2.714, f prime is negative. After 2.714, f prime is positive. So we know that that is going to make a minimum. So we're going to have a relative minimum there. And that would be because f prime changes from negative to positive. Alrighty, and then the last one, x equals 3.772. I notice that f prime changes from positive to negative, so we know that that is where a relative maximum would occur. So it's a relative maximum, and it is because f prime changes from positive to negative. All right, so far, all right. Okay, the next one, B, says use the line tangent to the graph of f at x equals 1.5 to approximate f of 1.8. So please notice they took something that was in chapter 5a for part A, and now all of a sudden we're back to chapter 2, I believe, or chapter 2 or 3 with the equation of the tangent line. So it says to use the line tangent to approximate this. Well, I can't approximate this if I don't have a tangent line. So we need to first of all find the tangent line, which you remember is y minus y1 is equal to mx minus x1. Okay, for this problem, I'm actually, since I'm dealing with the graph of f at 1.5, I'm actually given very nice information. So a point is 1.53. So we have our x and our y value, which is nice. Now remember, to get our slope, we need a derivative. So we need f prime of 1.5. Well, since we do have our calculator, I went ahead, I already had f prime in my y equals, so I went to the table and plugged in 1.5, and when I did that to 3 places, I got negative 2.103. All right, so notice I now have the point, I have the slope, I can plug stuff in, so I'm going to get y minus 3 equals negative 2.103 x minus 1.5. And then I like to bring the 3 over, so I'm going to have y equals negative 2.103 x minus 1.5 plus 3. All right, it said to use this tangent line, so now that I have my tangent line, I can use it to approximate f of 1.8. So now I'm going to say f of 1.8 is approximately, now we can just plug in 1.8 right there. So it's going to be approximately negative 2.103, 1.8 minus 1.5 plus 3. Okay, I would prefer to leave my answer right like that because then I have absolutely no chance of messing it up. But if you did go farther, we should get an answer of 2.369. So now that part's done. Okay, on to part C. This one says on the interval 1.5 to 1.8, f prime of x is less than 0 and f double prime of x is greater than 0. Is the approximation found in part B an underestimate or an overestimate for f of 1.8? Give a reason for your answer. So remember, we just found this, and it's just saying, was that an over approximation or an under approximation, right? We don't know what f looks like. We know what f prime looks like. So I'm just going to do a little kind of fake picture of this. It's telling us that the derivative is less than 0 between 1.5 and 1.8. That means the function is decreasing. F is decreasing. When f double prime is greater than 0, that means that f is concave up. So if I'm just going to draw like a little section of the graph, I know from 1.5 to 1.8, the function is decreasing and concave up. So it's going to look something like that. All right. 1.8 would be, I guess, right at the end of it. All right. So if I drew a tangent line, because it said we use the tangent line to approximate f of 1.8, the tangent line would be underneath the graph. So if the tangent line is underneath the graph, we would expect our answer to be an under approximation because the tangent line is under the graph. So I'm going to say this would be an underestimate. And I'm going to say because, I'm not even going to say because, I'm going to say since we know that f prime of x is less than 0, and, sorry, this is sloppy, f double prime of x is greater than 0, I'm not going to say the function, I'll just say f is decreasing and concave up, which will make our approximation an underestimate. Okay, so I guess we could have worded a little bit differently than that, but I'm pretty happy with that. All right, onward to part C. Okay, now notice again, totally different topic. Use the mean value theorem on the same function. Explain why the average rate of change of f over the interval 1 to 4 cannot equal 6.5. So I'd probably think like maybe it doesn't meet the conditions. So let's remember the conditions. The first one is that the function is continuous, and the second one is that it is differentiable. So they told us that f is a twice differentiable function. So they told us that it's differentiable, and we know that if a function is differentiable, then it must also be continuous. So I would say I'm just going to say f instead of the function because we know that the function is f. F is differentiable. I'm going to say we are given that f is differentiable, which means that f should also be continuous. So the mean value theorem should apply because we've decided that. Okay, but remember our third part of the mean value theorem is that somewhere the derivative is equal to the average rate of change. So we're trying to find out somewhere the derivative is equal to that average rate of change, which would be f of 4 minus f of 1 over 4 minus 1. I'm just using the slope formula on that one. Okay, so it's trying to tell us here that somewhere the derivative equals the slope. Well, they're just telling us that somewhere it's just saying it can never equal 6.5. So basically they're saying what we've been usually showing before. We usually show that if we can find the average rate of change to be 6.5, then somewhere the derivative has to equal 6.5, okay? But this time, since we have nothing about the function at all, we're going to have to try to go the other way. So this time we're going to have to see if f prime of 6 ever equals 6.5, then the average rate of change would also has to equal 6.5. All right, so if I remember we have a graph of what f prime looks like, which was, I'm just going to draw it again. It was something like this. We're just looking at, does the derivative ever equal 6.5? Okay, 6.5 is way up here. The line way up there, all right? Please notice that f prime never gets up as high as 6.5. So f prime never equals 6.5 on that interval. So it's not that the mean value theorem doesn't apply. It's just that if I find a spot where one of them is something, then the other one also has to be that. So the derivative never equals 6.5. So we are not, the average rate of change does not have to equal that. So I don't know how I want to say that. I'm going to come down here. Should apply, but f prime of x never equals 6.5 on the interval. So we're not really breaking the mean value theorem. It just never had the condition where we would even have to compare it to the other one. So hopefully that makes a little bit of sense. A little weird.